Is it recording?
Yeah.
Hello, YouTube. It has been a particularly rough week, so I'm wearing my pajamas. And I'm very tired. So let's do this. This is the third or fourth installment of the third installment of the Classical Mechanics Excellent Adventure series. So in this particular one, I'm not going to continue working on deriving further the theory that we had previously with the Lagrangian mechanics and moving into Hamiltonian. Instead, I'm going to derive something that's what I've found to be very, very useful, an excellent tool that I've only found in one of my classes and just slightly skimmed over. It's such an extremely helpful tool that I wanted to show the derivation here and also show a couple of applications and how powerful this thing was. So this is called the Virial Theorem. Have you ever heard of the Virial Theorem? All right, then buckle up. This is really good. So it's an extremely powerful theorem that allows you to answer a lot of questions about a system if you just know a couple of conditions that the system is constrained to. So first I'm going to do a proof because that gives you a little bit of understanding of why this thing exists in the way that it does. So consider a system of in particles. I'm going to label all of their coordinates by Ri. Then the Newton's law for this is going to just be the change in momentum of the ith particle is going to be equal to the force on the ith particle, where the momentum will be defined as the mass of the ith particle times the radius vector to that ith particle. All right, so we're gonna ask about this this seemingly arbitrary quantity, the summation over all of the particles of the momentum dotted with the radius vector on each of these. And what we're going to ask in particular about this thing is what is its time derivative? So if we were to just evaluate the time derivative here, we've got pi dot r, just by, we're going to use chain rule on this thing, plus yes, okay, so pi dot r plus pi dot ri dot. So the derivative of the first with respect to the second, all that stuff. And this thing can also be restated because the time derivative of the momentum is equal to the force. So we can actually just say that to be fi dot ri. And then this momentum can be expressed in terms of the mass and the radius vector. So we've got sorry, that's mass times velocity, not mass times the radius. That's a terrible mistake. This wonderful, beautiful quantity here. In this thing, since it's just the radius vector, the velocity vector dotted with itself, it's just equal to the velocity squared. It's just a dot product with itself, so it's squared. So you have the summation over all particles. Our first term, the force dotted with the radius vector, plus the mass of the ith particle times the velocity squared in this situation of the ith particle. All right, so what you can see here is that mv squared, if we define, we know that the kinetic energy we define as being 1/2 mv squared, so this term is equal to 2 times the kinetic energy. So we can already start doing a few little tricky things. If we put that in there. Yes. And then I'm going to leave this how it is for now, and we will come back to him in the near future. So now I'm going to introduce the average of a function over some range of values. So since I'm like 40 years old at this point, I don't know what freshmen and undergraduate kiddies know and what they don't know. So I'm just going to explain this as well. So let's say you've got a plot of y versus x, and you have some function f defined over this range of values. If you wanted to find the average value of f, it would just be basically, let's see if I've got a different color. If this were, let's say this value is the average value that f takes along this interval, we'll name this to be f of x within these little brackets here. And this distance here is going to be, let's just say it's over some range L. Then L times the average value of this region is equal to the area of this region if this were a rectangle of some sort. So we've got the average value is equal to the area over the length that you've got. And area, when we've got some arbitrary function, can be restated in terms of the integral of that function over that interval. Okay, so we can use that sort of thing here. And what I'm going to do in particular is find the average value of this thing on the left side. So we want the average of P dot R. And so that by definition over there is going to be 1 over, we'll just name this interval of time that we're going to integrate over to be tau. It's just going to be our integrated variable. Right. Yeah. Oh yeah, and then sorry, there's a dy dt that was out front of all of these things before. And this thing is, this is equal to the integral of a time derivative of something. So you can just evaluate this integrand at each of the boundaries. Just subtract, so the integrand evaluated at this boundary minus the integrand evaluated at the other boundary. 1 over tau, summation over I of, so we've got pi dot ri evaluated at tau minus pi dot ri evaluated at 0. That's just a fundamental theorem of calculus, something like that. Because these are inverse operations, the integral and the derivative, so when you have the integral of the derivative of this, you just take the integrand evaluated at both of the endpoints. Yeah, so now we can think real hard about this. So yeah, we have a system that I believe if I didn't tell you, I will tell you now. I will constrain the system because we're interested in systems in particular that are periodic. So if we've got basically some curve that is going to trace out something like this, so it's maybe a periodic orbit of some sort, just some system that repeats itself every amount of time. And let's define this tau variable, this average time over which we're averaging our integrand, is going to be the period of this. So every tau, it will return to the same exact location. So this p dot r is equal to the radius vector dotted with the momentum vector, which is going to be tangent to the trajectory. And since this is evaluated at tau and at 0, and you're subtracting the two, this whole thing just ends up being 0. It's the same value because it's periodic. The system returns to itself every tau. So cool, so the average value of this guy is 0. Good stuff. Yeah. And now we can go back to our neglected right-hand side of this whole equation, which was d by dt summation of pi dot ri is equal to that guy. Okay, so this is the thing that we had earlier derived, and if we want to take the average value of both sides, then the average value of this guy is what we just found to be 0, and this is going to be equal to the average value, the summation of the force dotted with the radius vector plus the average value of 2 times the kinetic energy. Since the average value of some constant times some other thing is going to be, that constant pulled outside, constant's not going to change, hopefully averaged over some region. If so, then your mathematics is horribly broken. Then you have that the average value of your kinetic energy is going to be minus 1/2 the average value of this term, the summed term. Okay, and I think this as it stands is not as intuitive as what I'm about to show you, but this is, I think, in general, what the Virial Theorem is. So this followed from very basic. All I did was just a bunch of calculus and moved some things around, and nothing extremely tricky yet. But we just have this relation between the average value of the kinetic energy over one of the orbits is equal to the average value of this other quantity. So now let's consider a system that we can use this to solve. So how about like a system where the force law is going to be proportional to some power of the radius. So for a gravitational force, it's going to be proportional to r to the minus second. It's proportional to the inverse square of the distance between two objects, which is also proportional to the Coulomb interaction, the distance between two charges. Hooke's law, for instance, is going to be equal to minus kr, which is going to be proportional to r to the first power. Things like that. So we're considering force laws of this variety. Then in this situation, we may express the potential as equal to the minus integral of force dot dr, which is just by definition. And since the force is proportional to r to the n, we have the integral of r to the n dot dr. And this whole thing is going to be proportional to r to the n plus 1, because of just how integrals work, because we have r and another r value. So it's basically r times r, yeah. So we're going to name this constant out front to be a r to the n plus 1. So we're going to say v of r is equal to a r to the n plus 1. So now we want to evaluate what this guy is on the right-hand side in terms of these sorts of things. This is sort of tricky because I'm trying to express everything in terms of potential energy. I knew where this was going in the first place, but just trust me, hold my hand through this argument, because it works out real fucking nicely. Since we're going to just evaluate this in the radial direction, this is only a radial force law, the vectors are going to be just dotted out like that. So let's see here. So this is going to be equal to minus r dv dr, because of just how the force is equal to the minus gradient of the potential. So it's minus dv dr equals minus r d by dr, and then we can insert what our potential was, a r to the n plus 1. And this is just a regular derivative. A can pull outside, and then this is just a regular happy polynomial derivative, which I can do without looking for once, is minus ar times, now we have n plus 1, which comes down, and then r to the n, which is equal to minus a n plus 1 r to the n plus 1, because we have this r here, and then the r to the n. And what we see here, wonderfully, is that we have an a r to the n plus 1, r to the n plus 1, a. So you actually express f dot r in terms of minus a v of r. Hopefully I have this. Oh, n plus 1, sorry. Minus n plus 1. That's the term that comes out. Yeah! So, delicious. So what we can do now is insert that into this equation here, and have that the average kinetic energy for this force law that is proportional to the nth power of r is equal to minus 1/2 times the average value of this summation. And this summation is going to be equal to n plus 1. We're just going to insert directly that definition for what we have here. V of r. Yeah, wonderful stuff. So n plus 1 can be pulled out of the average, which means now we have the kinetic energy is equal to minus n plus 1 over 2 average value of the potential energy. So this is actually in a state that makes so much more sense, and this is the directly applicable way that you can look at this formula. And to show you how absolutely fantastic and useful this formula is, I'm going to show you two examples. So a lot of classical mechanics and quantum mechanics problems can be solved using this form of the Virial Theorem, when it would be much, much more difficult to use force laws or anything else like that. So all you need for this to be true is you have to have a force law that's proportional to the radius vector to the n. That's where that n comes from. And you have to have a bounded system, just a system that's periodically going to return to its same location, which it happens a lot. In physics, we don't have many solvable problems. So the problems that are assigned for homework usually have closed form solutions or are solvable, and those are usually like bounded systems or periodic orbits of some sort. So we can use this to solve, we can do gravitation first. So gravity, the force due to gravity is equal to gmm over r squared, something like that. Yeah, in the r hat direction. Wait, it's actually minus though, right? Yeah, okay, so. Yeah, so we know that this force is proportional to r to the minus second. Right, yeah, so what this means is that n is going to be equal to 2, so we can just insert that thing in there blindly, and then we automatically know the connection between the kinetic energy and the potential energy of our system. All we had to do was just know that the force law is a scaling factor of n is equal to 2, r to the n power. And now we can just say that for gravity, for a bounded system, so basically if you have any body that's orbiting, a satellite orbiting some larger body, and it's periodic in some way, it's got a closed orbit, it's going to be equal to n plus 1, so that's 3, so minus 3/2 the potential energy. This is always going to be true. So with this relation now, we have an extra equation we can use to solve things. Yeah,
Would n be 2 or -2? 'Cause
yeah, you're the best. Thank you. I'm real bad with math, huh? Arithmetic. I think my notes even have it correct. I'm so bad, I should not even. Oh man, and there's another one too that, so let's see. So this was a minus force law, so that's a minus there. So this turns out to be a minus. So many terrible minus signs being tracked everywhere. This one's good though, because my notes agree, and I trust past self more than I trust current. So this is cool. So we have this law between the kinetic energy and the potential. So the kinetic energy we know that we can express as 1/2 m v squared, the average of the velocity squared. And if we, yes, oh, and the potential energy of the gravitational force is equal to minus g m over, well, I'll just multiply this out by the side, the average value of 1/r. So all of these things are constants, they pull out, so it doesn't worry about that in the average, but these are the variables within these. So we can re-express this Virial Theorem in terms of 1/2 m, average value of v squared, is equal to minus 1/2 times this. So that's minus sign, so it's equal to 1/2 g m, average value of 1/r. These little m's cancel, the 1/2s also cancel. So we have that the velocity squared is equal to g m 1/r. So again, we have this wonderful and very simple and straightforward equation that we've got just from knowing that we had a bounded system. We haven't had to do any like calculus really, except for in the derivation of this theorem. And we can get even farther and get more information out of this if we know that if we just say that this is a circular orbit. If we claim that this is a circular orbit, we then have that these average values are going to be the same value. 1/r is going to be equal to 1/r at all times. And then we also have that r dot, which is equal to v, is r omega, because if it's spinning in some direction, it's going to be traveling. So this is the velocity, this is theta, so if you define omega to be theta dot, the time derivative of theta, and you've got r d theta dt, yeah, you can express the velocity, the tangential velocity, in terms of the differential of the polar vector. Yeah, and that's equal to, so you know that omega, well hopefully you may know this, is 2 pi over the period. That's just sort of a definition, is the angular velocity is equal to, it's inversely proportional to the period with a factor of 2 pi for the phase. So now we've got r, well 2 pi r over tau. Good stuff. So then what we have moving down here instead is r dot squared is equal to 4 pi squared r squared over tau squared. Just renaming all those things. So we can put that in this formula as well. And I don't know if you're still able to see this down here? Okay. So we've got 4 pi squared r squared over tau squared is equal to g m times 1/r. And this, if we massage a little bit, or you can even just look at it how it is equal to 4 pi squared over tau squared gm over r cubed. Now I don't know astrophysics or all that fun stuff about space, but I'm pretty sure that's like that's Kepler's law, or at least one of the forms of it. And it's very interesting to see how that just comes out of here, because I did nothing. I did no work. I mean, you had to derive this in the beginning, but really all you had to know was this formula, or that one over there, and just know that n is equal to 2. And what you can do is you just plug in things that you know. You know that kinetic energy is 1/2 mv squared. You know the potential energy of a gravitational potential. And if you just know, like, the conversion between coordinates with things spinning and everything like that, you just blindly do this math and just chug through, and you get Kepler's law that falls out. So it's very cool and very natural to see the results of these. And my final example, this is fairly short because, again, I'm dead inside. Unfortunately, there's 2 proposals due a week from now, and it's making a lot of us very sad, because we have to do a lot of writing and a lot of science very quickly. All right, so now for something completely not classical mechanical, sort of. We're going to shove classical mechanics into it. The Bohr atom. So if you do the Bohr atom, or the Bohr model of the atom, you have the potential energy of an electron going around some sort of charge. So it's going to be equal to the electrostatic potential, 1 over 4 pi epsilon naught, Q1, Q2, whoa, over R. And, yeah, good. So if you have an electron and a proton, so just a little hydrogen atom, these are both charged E, so these both charges just end up being E squared. So you have 1 over 4 pi epsilon naught E squared over R. That's wonderful. So what we've got here is that the Virial Theorem, this is the same as gravitational potential. It's the force law is proportional to the inverse square of the distance between them, Coulomb and the gravitational force. So we have the same exact result for the Virial Theorem, minus 1/2 average of V. So we can just use this and get strikingly good results in quantum mechanics, staggeringly good. You'll see, it's really wonderful. So what we have for the left-hand side is the same thing as that 1/2 m r dot squared. It's just 1/2 mv squared, the average, is equal to minus 1/2, and then we'll just put that potential into here. So here, I'll just write it out a little bit more explicitly so that way I don't skip steps. So just inserting the potential right into there, I can reduce that a little bit better, is E squared over 8 pi epsilon naught, and value of 1 over R, 1/2 m R dot squared. Cool, okay, so now we just have this formalism, the exact same thing as what we've done over there, just blindly throwing in the potential and what the kinetic energy, what we know them to be. So now we can be a little bit trickier. This is where Bohr's quantization condition comes into this. If you just impose one condition onto the system that's purely classical mechanics at the moment, you can get a very good approximation to quantum mechanics, the old quantum theory. So you've got angular momentum is m, let's see, yeah, v cross r. Well, this could be considered r dot, so let's do that. And if this is a circular orbit, because that's just so much easier to deal with, I'm just going to assume that these electrons are traveling in circular orbits, then the cross product will always evaluate to be m r dot. Yes, good stuff. So that's equal to the angular momentum, L. So what Bohr did, and what was so fantastic and so wonderful, is he waved his hand so magnificently well. He was like a few inches off of the ground. He was flying. He waved his hand so hard with his derivation. It's amazing and it's so beautiful because it works. So what his quantization condition was for the old quantum theory is that he said, I don't give a shit what any our logic or intuition says. Angular momentum is now equal, I ordain it to be so, equal to some constant times this other constant. So integer values of some constant. So basically angular momentum may only take values of h bar, 2h bar, 3h bar, just whatever this constant is going to be that. So with this information, so yeah, here I'll write this out. And h bar is equal to mr r dot, because that was just our angular momentum. Yeah, so we want to find, it'd be nice if we could find what r dot squared is, so we could have something on the left-hand side and see if we get something wonderful like the Kepler's law falls out, something hopefully like that. So you got r dot is equal to n h bar over m r, so r dot squared is equal to h bar squared over m squared r squared times n squared. Hopefully that's all mathematically okay. And I can insert this into our Virial theorem that we're just going to cling to and see where it takes us. So we had 1/2 m r dot squared is equal to e squared over 4 pi epsilon naught, or 8 pi 1 over r. Okay, and then we can insert that r dot squared into the left-hand side. So we've got 1/2 m times h bar squared over m squared r squared n squared 1 over r squared is equal to e squared over 8 pi, a lot of constants everywhere, 1 over r. I hope that's still good. No, that r should have been, yeah, that's inside. Yeah, good. Wonderful stuff. So since we assumed the circular orbit, then the 1 over r squared, the average value of it, it's not going to be doing something weird like this or something like that. It's a circular orbit. So 1 over r at all times is going to be just the same value. So we'll just make these over r. Make sure I'm not doing anything crazy and terrible. Cool, yeah, I'm not. So good, so this is our wonderful equation now. So one of the r's cancels out from both sides. So we have 1/2 m h bar squared over m squared times n squared is equal to multiply r squared on both sides. 8 pi epsilon naught times r. And then we can just divide both sides by this whole thing. So we've got r is equal to 8 pi epsilon naught over e squared times 1/2 m, all these constants and things. I'm keeping them around because they're very important, actually, you'll see. You can cancel some of these things out, so that will turn into a 4. That dies. This m dies with that one. Yeah, that's stuff. So you've got pi epsilon naught h bar squared over m e squared n squared. Just to make sure I've got all of this wonderful and correct. Yes, good. Excellent. So this is wonderful. So now we have that the radius is going to be this constant. All of these are constants in here, times n squared, where n is the square of the value that the angular momentum can take. So we now know that the radius of this electron, if we impose Bohr's quantization condition, is going to be proportional to the square of this n value. And this thing in front is what we name to be the Bohr radius. So what we actually see is that the radius of a hydrogen atom, with this very shitty assumption in the Virial Theorem, and very straightforward, is a naught n squared. So what's really cool is that n is what we refer to as the principal quantum number. It corresponds to basically the shell number on the periodic table going down the rows. So it's very cool is that to a very rough approximation, the hydrogen atom, the expected radius that you would find something at is the Bohr radius, which this turns out to be about like 1/2 angstrom, times n squared, where n is going to be the orbital, the s shell's orbital. So that's pretty badass, because that just kind of falls out of this. Of course, you had to have Bohr's quantization condition, but without doing any real, I don't see it as being doing much real physics. It's just doing the mathematics, because we did the physics in just that assumption. Using the Virial Theorem and faith, you get the old quantum theory, and it's very nice. So with these two explanations of the Virial Theorem, I assume now you're good to just spread your wings and fly and use it in your own classes and things. But I highly recommend you at least look up what the Virial Theorem is and practice a few problems, just seeing how you can use it in your classes, because it's helped me a lot when problems otherwise would have been exceptionally difficult to do, because it gives you an extra equation in terms of scalars, energies, instead of vectors, which is always nice. So next lecture, I guess, is going to be what, Tuesday, say?
Mm-hmm.
All right, good. And that's going to be on, I think I'm going to be moving forward then with the material going into Hamiltonians, introducing the Legendre transform, what it means, what it's actually doing to a system, and then what the Hamiltonian is, like philosophically, what's going on with that stuff. So until next time, YouTube.